Hello, this is the introduction to the unit on gas laws. Going to be covering the first couple of pages of the gas law packet. So you should have the packet out and use it for a reference. Here's a quick little trivia question. Take a look at it, see what's missing. If you want, you can pause the video now, so this will stay up there, and you can decide what is missing. Let's do a quick review on the kinetic molecular theory. Kinetic molecular theory talks about gases and the movement of the particles. According to this theory, gas particles do not attract or repel each other. The particles are much smaller than the distances between them. Remember, the nucleus is very, very small, a lot of empty space in there. Gas particles are in constant random motion. They never stop, they just keep on moving. If they collide, one might increase in speed, but the other one has to decrease in speed. And their collisions are elastic. There's no gain or loss of kinetic energy. If they hit the wall of a container, it'll bounce back at the same speed. And also, all gases have the same average kinetic energy at the same temperature. That's the definition of temperature, is the average kinetic energy. Let's take a look at some of the variables associated with the gas laws. We're going to be learning a number of different gas laws, gas equations, and they will use different variables. We'll work our way until we get to the ideal gas law, which contains all of these variables. Let's take a look at the first one, pressure. Pressure is designated by a capital P, and there are a number of different pressures that can be used when we talk about pressure. The formal definition is force per unit area. Basically, the pressure exerted by the particles, how much force they have crashing against the walls of their particular container. If you look on your page 1 of the packet, you will see what force is, or what the pressure is. You can see there are different units: atmospheres, bars, millimeters of mercury, pascals, pounds per square inch, torr. Those are all possible units that you can use. You can also convert from one unit to another. Part of the exercise in this packet, you'll be converting from one unit to another using your dimensional analysis. But all those are the same. They're all equal to each other. You'll also see standard conditions. The standard condition is what scientists use to make sure everybody's working this problems the same way, doing all the calculations in the same way. Because pressure does change depending on where you are, depending on the weather, it'll change. So we need to have some sort of a standard system, some sort of a base to work off of. And this is what we have right here. All those are standard conditions, standard pressures. Let's take a look at volume. Volume is capital V, not to be confused with viscosity or velocity. Volume is the amount of space something takes up. So the size of your container. If you have a container of gas, it's at a certain size. That's what we're talking about. Temperature is our next one. Again, average kinetic energy is the definition of temperature. The units are in Kelvin. This is one of the most important aspects of gas laws. Temperature needs to be in Kelvin. Remember that. Really remember that. It's very, very important. Units are in Kelvin. The reason being is we cannot have negative numbers. We don't want negative numbers in our gas law calculations. All the other, the centigrade scale, Fahrenheit, they all have negative numbers. And if we end up using negative numbers, we'd have negative volumes, for example, which is not possible. So we have to use the Kelvin scale. Starts at 0 and goes up from there. 0 degrees Celsius is 273 K. Our formula, Celsius plus 273 gives us K. A lot of the problems that you'll be seeing throughout this packet are in degrees Celsius because that's what our thermometers read. Whenever we're in the lab, we're doing a problem, doing some sort of an experiment. Thermometers read it in Celsius. We'll need to convert that to Kelvin. So Celsius plus 273 will give us Kelvin. Our last variable is the number of particles, which is small n. Units are going to be moles. How many moles of that material do we have? Let's take a look at some of the factors that affect gas pressure. It's all about pressure, reading how much pressure we have for a lot of these gas laws. The amount of gas will affect the pressure, small n, number of moles. If you have an increase in the number of particles, you will increase the pressure. Think about blowing up a balloon. You blow up a balloon, it gets full of air, you're adding a lot more particles to it. And that's why the pressure inside the balloon is greater. You're adding more particles to it. Volume. If you change the volume of the gas, you will change the pressure. Volume needs to be in liters, capital L. A lot of our things are going to be in milliliters because that's what our graduated cylinders read. So liters for the ideal gas law, we'll have to have. Some of the other gas laws we can use milliliters, but for the ideal gas law later on, we'll need to have liters. If you decrease the volume, you'll increase the pressure. So again, think about a balloon. Take a balloon, squeeze it. You're decreasing the volume of that balloon, so the pressure increases. That's why your balloons will pop if you squeeze them. Temperature. Again, temperature is in the units Kelvin. If you increase the temperature, you will increase the pressure. If you heat something up, it'll get larger. To that activity last unit with kinetic molecular theory, talked about putting a balloon outside in the cold. It gets smaller. That's because the temperature was reduced. You reduce the speed of those particles, so it reduces the pressure. But if you increase the temperature, the particles move faster. There's going to be more collisions with the wall, and those collisions are going to be harder. So that's why increasing the temperature changes the pressure. Particles will be moving faster. Take a look at our packet. Do one of the examples. 125.3 kilopascals to torr. We need to figure that out with dimensional analysis, just like we always do. 125.3 kilopascals. We need to go to torr. So we need kilopascals in the denominator, torr in the numerator. Then what we need to do is look on the first page of our packet and look what those standard conversion factors are for standard pressure. We see that it is 760 torr and 101.3 kilopascals are equal to each other. When we do this calculations, our kilopascals will cancel out. We will end up with our units of torr, and we will get 940.1 torr for our answer. So in your packets, after this introduction, you'll need to start looking at those first couple of pages, doing the conversions between pressures and conversions between temperatures. One thing I forgot to mention about temperature, standard temperature. I talked about standard pressure before in that packet. Standard temperature is 0 degrees Celsius or 273 K. That's their standard condition. Again, scientists need some sort of a temperature to use as a base, and they chose 0 degrees Celsius or 273 K as that base. And that concludes our presentation.